Hello everyone, this is our sixth tutorial. So let me solve a few problems. Question number 1. Is given which of the following are correct. F is continuous if and only if option A, f of A closure containing f A closure. B, f is open. C, f is closed. And option D, option D is different. This is for problem 1. Option D says not D, it is second part. It says give bijection plus cosine, that is equivalent to homeomorphism. If it's continuous, it is already given. Now it says this is B, C. It says if is continuous given, then bijection and cosine if and only if is homeomorphism. So let us see which of these are. So option A is correct by definition, right? F is continuous, then f of A closure. This is an equivalent way to formulate continuity. This is true for all A containing X. Now, what about option B? F is open, is it true? So continuity may not imply it is open. Option B, it is not true. For example, we have previously seen that this map, sorry. So we are considering these topological spaces, this topological space, this union with, so X is our topological space, right half plane, that is all X comma Y, this belongs to R2 with X greater equal to 0, and this is one possibility, and another one is or Y equal to 0. So this is same as saying upper half, right half plane union the x-axis, right half plane union x-axis, union with x-axis. Both are x, but this is for x-axis. Now, if we consider the function f map x to real number, just project everything x comma y to x, that is for any point x comma y, it is projected down here on the real axis, x-axis. Now we have already seen this map is continuous because the projection map pi R2 to R, this is projection map defined by pi of xy equal to x is continuous. Why? Why this is continuous? Because we can see pi inverse of some u. This is actually u cross r. So if u is open, this will imply u cross r, that is pi inverse of u is open. So pi is continuous. And now f is nothing but, we have just restricting this map on this domain, right? We have changed the domain. So since f is restricted on, so the domain is restricted on x, f is obtained by restricting the domain of pi. So it is restricting mean it is nothing but this. So f is nothing but this inclusion x inclusion in R2, which is always continuous. We have already observed this thing, and now R2 to R we have projection pi, right? And this map, this is the inclusion. This map is x. So composition we can also see in this way. F is composition of f equal to pi composition inclusion, and both are continuous. Therefore, this should be continuous, right? So f is continuous, but f is continuous. But we can observe that f is not open. Why? F is not open map, not an open map. Why? Because if we take this was also done in previous class. If we take this open set, this sorry for the interruption. So f is though f is continuous, f is not open. We can observe this fact because uh, if we consider this upper half portion, that is consider upper half portion xy belongs to x such that x y is positive. That is this part, right? This upper half part, and I have not included this x-axis. Then this is open in the subspace x. This can be written as intersection of this some open set dot 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 this kind of open set, this intersection with x. Okay, this will give this upper half, and it does not have any boundary on the lower portion. So this is the reason. This is though this is open in x, but its image, if we see, the image will be this portion, right? It will be from close 0 to infinity. we are taking this part. So its image, everything will land here. So it is from close 0 to infinity. So f of u is close 0 comma infinity, which is not open. Therefore, B is not true. Now, what about C? C is also not true. The same example, same kind of example will work. Same map, take the same map f from x to r. Now consider this graph, right? Y equal to 1 by x. F, let f equal to this. This is our u equal to this. So here choose f equal to x comma 1 by x and x greater than 0. Then this is f is closed in x, right? This set is closed in R2, therefore it is also closed in the subspace. Okay. Now, why this is closed in X? It should be clear, right? Because it contains all the limit point. Therefore, it is closed. You can also see in this way that complement of this part is open. There is a more general theorem. You can use that also. That if graph x comma fx if we consider this as a subspace of R2, then that will be closed. If f is a continuous function from R to R, so this is not the case here, but it is easy to see this arc will be this graph will be closed because it contains all the limit points. So though this is closed, but image of f this will never touch the origin, right? Project everything here, so it can never touch origin. It is open 0 to infinity, and this is not open, sorry, not closed in X, in real number, in the image codomain. So we have chosen a closed set whose image is not closed, right? Therefore, F is not a closed, closed, open map, closed. Now, what about bijection plus cosine? Is it equivalent to homeomorphism? Even F is continuous now. Then is it true that bijection plus cosine? So B and C, those two are not true. A is true by definition. That is one of the equivalent condition. We can prove this using F inverse of U is open if and only if U is open by this criteria. Now, what about option D, bijection plus cosine D? Given F is continuous, now F is also bijection and cosine. Then will it be true that F is homeomorphism, and what about the converse? So converse is easy to see, right? Something is homeomorphism means there exists a map in the reverse direction such that G compose F is identity and F compose G is identity. So these two will imply that F is bijection. So F is homeomorphism will imply F is bijection. This is clear. Now what about quotient? F is homeomorphism. Therefore, F inverse is continuous. So F inverse U is open for all open set U, right? Now F is homeomorphism, that will imply there is a map in the reverse direction. Okay, so that will actually imply that F should be open map. Why? Because if we take an open set U and apply F, then we need to show that this should be open. Okay, but if we again apply G, GFU is same as U, right? So because G compose F is identity, therefore Fu can be written as G inverse U, but G is continuous, right? So inverse image of continuous, inverse image of open set under continuous map is open. Therefore, G inverse U is open. Hence, F is open. Okay, Fu is open. There, so we observe that homeomorphism imply open map, and open map is always a quotient. Right? Therefore, option D is correct. So for option D, homeomorphism will imply continuous bijection plus open, and the reverse is also true. Okay, and open imply quotient. Similarly, we the reverse direction will be also true. Okay. Now let us see question number 4, 5. So, which of the following are invariant under homeomorphism? Option A is length, option B is boundary, option C is separability, option D is first countable property. Let me write another option, house dot property, T2 property. So we have already seen that length is not invariant under homeomorphism. For example, we have seen that if we take this map 0 to infinity, that is fx equal to, consider that same map, fx equal to 1 by x. So image will be like, the graph will be like this. So sorry, here I think I have said something. The image means, yes, it is okay. So in this case, we can see that this map, if we define this map from this 1 0 to 0 comma infinity, 0 comma 1 to 1 to infinity, that is, my domain is this sorry, open 1 to infinity. Okay, this is my domain. Then we can see the, oh sorry, my domain is this 0 to 1, this interval 0 to 1. So its image will be like this. So so its image will be this, from this 1 to infinity, right? This 1 to infinity. And we have this, it is easy to see that this f is continuous. We already know this map is always continuous because uh, denominator does not vanish there. So those kind of division is always continuous. F is continuous, but what is the inverse of f? The inverse is same. So we can define the map in the reverse direction g, define g of y equal to 1 by y. And we can check that f compose g and g compose f both are identical. Therefore, f is homeomorphism. Homeomorphism. Right? Now, what about uh, length? Length of the interval is 1, but the length of this 1 to infinity, this is unbounded, right? So length of domain equal to 1, and codomain, it is unbounded, okay? Infinite. Therefore, length will not be preserved under homeomorphism. Now, what about boundary? So again, topological boundary will not be preserved under homeomorphism because boundary depend where you, for example, boundary depends on the source where you are, where the space belongs. That is, if we consider this open 0 1 as a subspace of R, then boundary of this set, boundary of this set, uh, it is this 0 and 1. Both are boundary point because boundary, we know that boundary is same as closure minus interior, right? So A is not true. Now what would be? Now let us again consider f A equal to the same 0 1 but as a subspace of this R2, okay, as a subspace of R2. Now what will be the boundary of A? Boundary of A, this is now closure of A minus interior of A. So what will be closure of this open interval 0 1? It is closed 0 1, right? Now what about interior? We can see those points are now not interior. Previously as a subspace of R, those are interior point. Because take any point here, you can always find an open neighborhood which containing this open 0 1. But here, if we take any point, now the neighborhood will look like this, right? Neighborhood will look like this open disk, and open disk cannot entirely lie in this set A, right? This cannot be possible. This is open disk, and there are lots of points which does not belongs to this interval 0 1. Therefore, interior is empty. minus empty set. So boundary, everything will be a boundary point. So boundary is not preserved under homeomorphism. Those two, those two are same homeomorphic set, but I am viewing this set as a subspace of R, and this set as a subspace of R2. Then we can see the boundary are different. Boundary depends where the subspace is. Okay, so boundary is not preserved. Now, what about this T2 property? We have earlier seen that Hausdorff property should be preserved, right? Because this is for B, for A, of option E. So F is homeomorphism. Homeomorphism. Suppose suppose X is Hausdorff. X is Hausdorff. Hausdorff is denoted as T2 property. Then take any two distinguished point X and Y, different point, then it can be always separated by some open set U and V. Okay, there are some open set U, V such that X belongs to U, and for all X not equal to Y in X, there exists U comma V open set, disjoint open set, disjoint open set containing X comma Y, those 2 points. Now what can be done? So now we okay, this is the definition of Hausdorffness. Now we want to use this property to for separation of any 2 point in the codomain. F is a map from X to Y. Let X is Hausdorff. We want to prove Y is also Hausdorff. So take 2 point Y1 and Y2. 2 point from Y and Y1 not equal to Y2. Then just take the pre-image F inverse Y1 and F inverse Y2. Okay. Since Y1 and Y2 are not same and F is a bijection, therefore the F inverse of Y1 and F inverse of Y2 will be different since F is bijection. It is also true even if F is not bijection, then those two sets cannot be same, right? Two different set cannot be mapped to that is two same point cannot be mapped to different point. So this is also true for any general case, but here F is bijection, therefore F inverse Y1 and F inverse Y2 both are singleton set, that is point. Those 2 points are different. If two different points in X. Therefore, we can use this property. For any two different points, we can choose two open set which separates those 2 points. Disjoint open set. So there exists U1 and U2 containing those 2 points such that their intersection is empty. Now apply F. So containing those 2 points mean these 2 points. Okay. Now F of U1 and F of U2, this is those 2 points respectively. By Hausdorffness by T2. Since X is T2, Therefore, this will be true. There exists some open sets U1, U2. Since F is homeomorphism, F is also open map. Okay. So if U1 and if U2 both are open sets, and note that those two open set contains Y1 and Y2 respectively. And also note that F is open map, therefore this from here we will derive that this is also non-empty, right? Because f of A intersection B, we are using the property f of A intersection B sorry. Suppose something belongs to some y, x belongs to y1 intersection y2, then x belongs to y u1. That imply fx belongs to f of u1. Similarly, x belongs to u2 imply fx belongs to f of u2. Therefore, fx, that common point, will belong to both sets. Therefore, this is non-empty. That implies this is also a non-empty set. Okay. Hence, the conclusion follows. So one part is clear, that x is Hausdorff imply y is Hausdorff. Now again, by homeomorphism, use the map in the reverse direction. Okay, there exists a map in the reverse direction. Using the same argument, we can prove y is Hausdorff imply x is Hausdorff. Therefore, T2 is preserved under homeomorphism. Now, D said, what about fast countability? So again, the answer is yes. The idea is similar. That is, this is more than that. If suppose f is a map from x to y, this is continuous plus open map, then the image fx, that will be also fast countable. Given x is fast countable, then those two are enough to say that fx is also fast countable. Okay. So the idea is easy to see that why this will be true. Fast countable means we need to find local basis, right? Any for any point. Suppose f is, suppose x, this is fast countable. Let x is fast countable. Then we will assert that y is also fast countable. How can we see this fact? So fast countable means for any point y belongs to y and any open set u containing y, u is open in y. We need to find for any arbitrary point for a fixed y belongs to y, at each time we need to find a collection of countable open set. So some bn, n belongs to it. This depends on y. So we may also write bn comma y, this kind of b n comma y, this kind of open set we need to find, or bn square bracket y. such that y belongs to BNY, which is contained in Q. We need to show this fact, right? So we can use the fact that uh, uh, if is continuous, so for any given point y and a given point u, take the inverse image f inverse u. This is open. Okay, let this y belongs to y and u is an open set containing y. Then f inverse u is open. Now use the fact x is first countable. So there exists some b n. Consider any pre-image of y. Take let f of some x0 equal to y. Then then for this x0, there exists this collection, right? N belongs to n, such that x0 belongs to Bn x0 containing f inverse. Now just apply f. So fx0 belongs to f of Bn comma x0 containing. So this is the desired Bn. Okay, and we are using that f is since f is homeomorphism, f is also an open map. Therefore, f of this open set, that will be open. Similarly, you can also prove that second countability property that is also invariant under homeomorphism. So, if one of these is second countable, then another one will be also second countable. And the similar kind of statement is true for separability. So those are actually called topological property because those are invariant under homeomorphism. Okay. So this is true, we have proved. This is also true, we have proved, and this is exercise. You can check the similar kind of idea. So you choose some kind of open set, some kind of set. You just translate, apply f, and translate in y. Okay. So, what is separability means? Separability means there exists some countable dense set, right? Let us see. See, uh, let X is separable. X is separable topological space. Then there exists a countable set Xn. N belongs to N. There exists a set, so denoted by which equal to S. Say, then the closure of S will be X, right? So we use this property to prove. So we can prove that Fs closure, just apply F on those points. So applying F will get Fx, so that N belongs to N. This set will be dense in Y. Okay. So there exists a countable dense. So if one is true for X, then that will be also true. Okay. F of S closure, that is same as Fs whole closure, because uh, we know continuity means F of A closure containing Fa closure, right? But for homeomorphism, this is actually equality. because you can prove the similar kind of thing for G also, and G is same as F inverse. That is, you can prove that F inverse of A closure contain in F inverse of A whole closure. Okay, you can use this fact to prove that uh, F of A closure is same as F a whole closure. This is an exercise you can check. So from here you can say that separability, that property is also preserved under homeomorphism. So Fs is nothing but this set, right? Fs Fxn n belongs to A, which is a countable set. So this is also. So we have seen some properties are topological properties, that is preserved under homeomorphism, but some properties are not. Now there is another question. So question 3, it is similar to the question 1. It says, suppose F is quotient map, which of the following are correct? Option A, F is quotient map imply open map. Option B, quotient imply closed map. Option C, this says closed imply quotient. Okay. And D says uh, closed imply quotient, maybe open imply quotient, and closed imply quotient. Which of the following are correct? So we have constructed a counter example for question 1. The same example, the same map, that is, recall that map. F is from x to r, and it is given by the projection f of x comma y equal to x. You can see that, you can show that this map, x is this domain, this union x axis. Okay. Oh, sorry. So you can prove that this is a quotient map. We have already proved this is actually a quotient map. But as in question 1, f is neither open nor closed. So those two are false. Now what about C and D? C and D, those are actually true. F is open imply. Uh, so C and D are also not true, because open may not imply quotient map. We need some extra additional property. There can be some open map which are not even surjective, right? For example, consider the inclusion map. R containing R2. Not this. This is not actually open map, but we may consider something like this. R2 maps to R2, where x comma y goes to, no, this is not actually open map. So we should be able to construct some open map which is not even surjective. That is the issue which will arise. Let us try to consider an open map. which is not surjective. C is not true. Similarly, D. Consider the inclusion. Open 0, 1. This included in R. Okay. F maps this. So f of x is, that is, maps identical. Inclusion of the open interval. Then we can see this is actually open map. Take any open set, it maps to some open set because it is identity map. Whatever open set we choose, some even some interval a comma b, this kind of basis neighborhood, this is same as ab. Okay, so image of basis element is open, therefore image of open set, that will be also open, because open set is nothing but union of those kind of basis element. So here we can see that f is not even surjective. So this f, this is open but not even surjective. Therefore f is not quotient. The same thing we can use similar kind of example f from this closed 0, 1 to r. The same math, f of x equal to x, d is also not true. So none of the above. None of the above. Now, can we modify the conditions such that open will imply quotient map? So, modification of this problem. So, if f is continuous plus surjective, then open or closed imply f is quotient map. Okay. So why this is true? Let me prove for open. Open imply quotient map. So we need to see that f inverse of u open if and only if u is open. So let me write in this way. F inverse is open. F inverse u is open. Then since f is open map, therefore f of f inverse u, this is open, right? But f of f inverse u is nothing but same u. Therefore we have proved that f inverse u is open imply u is open, and the converse is true by the property of continuity. Converse is directly follows from continuity. Conversely, u is open, then this is since f is open map. U is open set, then f inverse of u, this is open. This is since f is continuous. So therefore we are getting this condition, f inverse u is open if and only if u is open. This is if and only if condition. Given continuous plus surjective additional assumption. Okay. Then open is same as open imply quotient. Sorry. Therefore, this is the therefore f is quotient. F is a quotient map because we have proved that f inverse u is open if and only if u is open. Okay. Now there is another one question. Question number 6. Which of the following are correct? Option A. This says that uh, second countability imply first countability. Option B says the reverse direction, first implies second. Option C says uh, matrix space imply the space is second countable. Option D says matrix space imply separable. There are more options. Separable imply fast. F says fast countable implies separable. So just recall this fact. It is already done in uh, one class, in PTL class. So we can also look from this Moore's book. Separable will imply both. Second countable will imply second countable. That will imply first countable property. Because countable existence of countable basis, that will give existence of local basis. This is obviously true. But and second countable will also imply first separability. Right? Something is second countable. That means it is second countable implied. Is it true? Okay. This is also true. You can look at the proof. This is not that much straightforward, but you can look at the proof. So this second countability will imply first countability. This is by definition, and second countability will also imply separability. But other relation are not true. That is first may not imply separable. There is no implication. First may not imply separable. Separable may not imply first, and the reverse direction are also not. So let me give some counter example for those facts. So we have seen that before that is matrix space implies second countable. So matrix space may not be second countable. We have seen some example. For example, R real number with discrete matrix discrete metric. So that is same as saying discrete topology. So that is not second countable. Though this is a metric space, this is not second countable. And this example also shows that there is no countable dense subset, because whatever subset you choose, that is itself closed, because this is discrete topological space, so every subset is actually closed. So whatever countable set you choose, the closure of that set will be itself. Okay, so metric space may not imply those two properties. The same example, this is not second countable and this is not separable. We have also seen this fact in previous days class. Now what about separable imply fast countability? So that is also not true. So this direction is not true. Fast, for example, here this is actually fast countable. Though this is not second countable, this is actually fast. And also metric space is always fast countable space. This is actually fast countable. This is though fast countable, it is not second countable. So fast will imply second is false by the same example. This is false. The same counter example for B, C, D, for option B, C, D. And now what about separability imply fast countability? So again, separable space may not be fast countable space. That example is also observed, right? For example, R with that R with lower limit topology. This is actually this is for option E. This is actually separable space, right? Why this is separable? Because what will be the closure of Q? Q is a subset. Closure of Q, that is, yes, closure of Q in this space will be R, right? This example is, earlier we have observed this example. Sorry, that is not the example which was considered. R with lower limit topology. R with lower limit topology is actually fast countable. That is R with cofinite topology. Cofinite topology. This is actually separable. Why? Because cofinite topology means all the closed sets, there are only two possibility of being closed. So closed sets are explicitly finite set. Only finite set are closed, or there is only one option R. It should be the whole set. Therefore, what will be the closure of Q? By definition, closure means intersection of all those closed set which contains Q, right? Closure of this rational, this is intersection of all closed set containing Q. But we can see finite set cannot contain rational, because rational is countable even infinite. It contains countable even infinite numbers. So the only set which contains Q is only closed set which contains Q is R. Therefore, closure of Q is R. So there is a countable dense set, right? Q is countable dense set in R with cofinite topology. So therefore, this is separable. R with cofinite topology, this is separable, but we have observed that this is it is not fast countable. This proof is trickier. This part is easy, that why this is not separable, but this is not why this is separable, but this is not fast countable. Here there is slight trick, but we have already proved that fact. It is easy to observe that uh, this is not possible, but to prove this, it is slightly difficult. Okay, difficult than this, but not that much. You can prove. Earlier day we have already proved that. So separable will also separable. Um, there are some fast separable space which are not fast countable. So this direction is false. Now fast countable imply separable space. This is also false, right? Why f is false? F is false by the same example. This example will also work for it. This counter example. Here we can see that R with discrete metric, it cannot be separable. We have already seen, but this is fast countable. Okay, just for any point x, choose the open set that is local basis x, which is singleton set, hence countable. Countable means there are two types: countable infinite, or it can be finite set also. So 6 is easy. So those are actually, there are lots of different examples, but you should always remember this kind of, those examples are standard. R with discrete metric and cofinite. Those counter examples should be remembered. Now, question number 7. Which of the following space are metrizable? Option A, R with discrete topology. Option B, R with lower limit topology. Option C, R with topology generated by the basis A comma infinity, where A belongs to R. So in previous class, I have mistakenly said this is actually a topology, but this is not a topology. The problem is arbitrary union, that R, I have not written R. So if we include R or this A comma infinity, then this is topology. So that should be corrected. And option D, R with cofinite topology. So metrizable means you can provide a metric space structure on that topological space. That is, X is homeomorphic to a metric space. Okay. So in discrete space, open sets are with discrete topology. Here the open sets are generated by those singleton set, right? Are with discrete topology, open sets So basis is the open set. Every set is open set. Okay, open sets are any subset of R is open. Now, can we find a metric which gives this structure, which will generate this topology? So consider the metric dx comma y. Dx y, this is 1 if x equal to y and 0 if x not equal to y. Then the open ball, so this generates a topology, right? Matrix topology is generated by this kind of open ball, bx comma r. So x belongs to x and r belongs to some positive real number. Generates a topology. Generates a topology. This is the metric topology generated by this metric D. Now the thing is that bx comma r. There are two possibilities. If r less than 1, then what are the distance from y to x? Whose distance, what are dy comma x less than r? Now r is less than 1. Maybe take r less equal to 1. In this case, this will imply uh, distance is less than 1, strictly less than 1. This will imply the only possibility is 0. Distance is either 1 or 0. But 0 occur, sorry, I have said something wrong. Distance from itself should be 0. So x equal to y, that is 0. And for x not equal to y, that is 1. So this possibility will occur if and only if x equal to y. So the only thing which belongs to this ball is the singleton set. Now if r is strictly greater than 1, then choose all those y such that distance from x is less equal to 1. And this is true for all those sets. Right? Distance less equal to 1 means it is either 0 or it is equal to 1. So all points belongs to this bxr. Now x means actually the real r is the domain. R is the set under consideration. So here it is clear that this bxr, this will generate this topology, right? Because those are any take union over. So suppose S is a subset of R. S can be written as union of the singleton set X. X belongs to S. Therefore, any arbitrary subset, any subset of this R is open with respect to this basis. Okay. Hence, R with discrete metric is actually discrete topology. This is actually metrism. Now, what about lower limit topology? So, lower limit topology, there is a problem, right? We have seen that lower limit topology, this is not second countable. Earlier day, probably we have seen that, yes, earlier day we have seen R with lower limit topology, that is a non-example of second countable. So, but second countable metrizable, we have also seen metrizable does not imply second countability. But there is a thing which says that metrizable plus separable, that will imply second countability. So that is an important theorem or lemma, whatever you say. For B, metrizable plus a space which is metrizable, and if it is separable, that too will imply second countability. That is second countability. So for B, we have just earlier we have observed that R is actually sorry, R is actually separable, and also it is R is separable because R can be written as closure of Q. So R is separable, and R is separable, and if we assume this R with lower limit is metrizable, then that will imply R with lower limit topology should be second countable. But R with lower limit topology is not second countable. R with lower limit topology is not second countable. So if we assume R with lower limit topology, if this is metrizable, since R with lower limit topology is separable space, then those two will imply this, which is a contradiction. Those two will imply this is second countable, but this is not second countable. Therefore, there is some mistake. The mistake is this is metrizable. So therefore, R towel is not metrizable. Okay. So this is the problem where this is the real problem in this case. So this option is false. Now, what about topology generated by this kind of basis? In this case, we can see for option C that this kind of ray topology, so open sets are given by this interval. This is not even Hausdorff. But if something is a metric space, then this should be Hausdorff space, because for metric space, for any 2 point, we have earlier we have seen that those 2 points can be separated by this open ball. Take the radius as x, distance between xy, and divide it by 2. So half of the distance, those two open ball will separate those 2 points distinct. But so metric space, a side note, metric space imply Hausdorff property T2, but this is not Hausdorff. Hausdorff is denoted by T2. Therefore, so this ray topology, the topology R with ray topology, I am calling it ray topology because open sets are that will look like this kind of ray. So this is not Hausdorff. Okay. Therefore, it is not metric, because metric will imply it is Hausdorff. Since it is not Hausdorff, so it cannot be metric space. Now, what about R with cofinite topology? So we have already observed that a metric space will always imply first countability. So again the same, by the same argument, R with cofinite. So metric, this is not true because metric imply first countable space. Okay, so those are some important, you can use some important fact or observation to solve those kind of problems. Now one problem is from cosine topology, and okay, so is it true or false? The question says we have already seen that product preserve Hausdorff property. If x and y are Hausdorff space, then their product is Hausdorff. And similarly, if the product is Hausdorff, then the space, both space x and y, those will be Hausdorff space. But what about quotient? Let so the statement says x is quotient map preserve Hausdorff property. Is it true? So answer is false. This is not true. Why this is not true? So consider this quotient map. R some R with usual topology. If something is not written, then always assume that is usual topology. And consider the space y with tau. So here y equal to a comma b, and define the map f. So we want define f as f of x equal to 1 if x greater or equal to 0, and it is 0 if x less than 0. Then can we topologize y such that this map becomes a cosine map? So the answer is yes. So how do we topologize? We'll define something will be open if and only if their inverse image is open. So can this one, can it be open in y? This is open in y. Is it possible? When we want this f map, f maps a cosine map. So if we say one is open in y, that by property of cosine map that will also imply f inverse of this one is open in x, open in this domain. But f inverse of 1 is this closed 0 to infinity, which is not open in real number, open in R. So sorry, AB, so that should be written as A, and that should be, so therefore A is not open. A is not open in R. A is not open in Y. What about B? Is B open in Y? We want F to be a cosine map. So if we can we assume B is open in Y? This should be open in Y if and only if that inverse image of this P is open in X. So we see that inverse image is nothing but minus infinity comma 0, which is open interval in R, open in R. So A is open. The only open set is A, and the whole X should be also open, right? So the topology tau, that should be empty X and the singleton set B. Because F inverse of X is whole R, which is always open. So those are the only open set in uh, this. Sorry, this is not X. This is actually Y. So those are only open set in Y. So if we define F in this way, define Y with respect to the topology tau with respect on Y in this way, then this F becomes a cosine map. You can see F inverse of those sets are open, and F inverse of something is open, that will imply F inverse of Y is open, that imply Y is open, which is okay. F inverse of B, which is open, that imply B is open, which is already assumed. So in this way, we see that F is cosine, but is F preserved? Does F preserve this Hausdorff property? So on the left hand side, R with usual topology, this is metric space. Usual topology, this is Hausdorff. But what about Y with respect to this topology? So here we cannot separate 2 points. A comma B, those are two different points, right? By definition, those two are different points. It is already given. A not equal to B given. So A not equal to B, those are 2 points in Y, but there does not exist open set, disjoint open set which separates A comma B. Okay, so the only non-trivial open set is B. So you cannot expect A also belongs to this B. So there is no other open set. The problem is there is not enough number of open set. So quotient of some Hausdorff space may not be. So Y comma tau, this is quotient map. So this is actually this can be thought as a quotient space of this topological space. Though this side is Hausdorff uh, space, but this is not Hausdorff. Okay. Question number 9. Which of the following are correct? Option A, R is homeomorphic to S1. Option B, S1 means circle, unit circle. S1 is homeomorphic to this set. Two circles are identified at this point. Okay, this is sometimes called figure 8 space. Figure 8 because it looks like 8. Figure 8 space. Or there is a better name, it is called wedge. Wedging at a single point. Wedge of two circles. Option C, S1 is homeomorphic to real minus 0. Option D, A comma B homeomorphic to closed AB. So which of the following are correct? So to solve this problem we need something about connectivity. Okay. So there is another one topological property which can be useful to distinguish two topological spaces. Okay. So let us first discuss that property. Connectedness. a topological space X is called connected if X can't be partitioned into two disjoint open set. For example, if we see X equal to this space 0, 1, 2, 3. So X equal to this union of these two intervals. Okay, 0, 1, union 2, 3. Union of these two open intervals. Then it is clear that X can be written as union of two open set, disjoint open set. 0, 1, union 2, 3. Those are disjoint open set. As it seems from the picture, it is actually disconnected. Now what about this space? 0, 1, 1, 2. Y equal to this space 0, 1, disjoint U. So again, those two are open set. This is open, this is open. So I am considering subspace topology of real number, real Euclidean topology or real usual topology, whatever you say. So again, Y can be written as disjoint union of open set. Therefore, Y is disconnected. So this is not connected. This is not connected. Those are two counter examples. Now, what about open 0, 2? So open 0, 2 can be written as 0, 1 union closed 1, 2. So those are disjoint set. But note that first one is open. This is not open. So I am saying that this can be broken into two disjoint open set. So though those two are disjoint, but that is not two disjoint open sets. So you cannot broke this from the picture. It seems that we cannot broke this interval into two disjoint open set. Okay, that is also true. We'll see in the next tutorial. We'll solve some problem based on that. That is actually that comes from intermediate value property. That this kind of interval is always a connected set. Okay, you cannot broke it into two disjoint open set. This is open, this is not open. So this kind of set is always connected. Any interval of this from A, B is connected. Now, how this helps to distinguish two topological spaces? So the thing is that if X is connected and F is a continuous map from X to Y, continuous map, then the image F of X, that is also connected. Okay. Note that connected means disconnected is more easy to define, because disconnected X is disconnected means X can be written as disjoint union of two open set. Here disjoint open means I always assume that those are non-trivial open set, non-trivial. So non-trivial and the whole set, that is disjoint open set means empty and R. Empty and the whole, those two are not allowed. Okay. Then we call the space X is connected. So that is why, in particular, if F is homeomorphism, then the image of X, F is homeomorphism, then the image will be the, that is onto map, bijection is therefore onto, then Fx which is same as Y. So X is connected will imply Y is connected. Similarly, Y connected will also imply F is X is connected. Okay, so that is why the property connectedness reserved under homeomorphism. And the interesting thing is that we can do some more. That is, we can disprove that two spaces are not connected. For example, this open interval open 0 1 is not homeomorphic to this closed 0 1. Why? Just remove a point. So removing a point, this will remain connected. But removing a point, whatever point you remove, it will be broken into two parts. 0 comma some. Suppose we remove the point P, then this interval will be broken into two parts. This open interval 0 comma P union this P comma I. So that can be now written as, if we remove this point, this can be written as disjoint union of two open interval. Okay, non-trivial means those are non-empty and not the full set. And also observe that disconnected, this actually means this is equivalent to having a non-trivial closed set which is also open. There exists a set which is non-empty and not the whole set, which is simultaneously open and closed. Okay, so this is one of the, you can see if something is connected or not, because disconnected means X can be written as disjoint union of open interval UV, those are disjoint. So suppose U is disjoint, therefore U is by definition U is open. But we also note that U can be written as X minus V, because those two are disjoint. V is open, therefore the complement, this is actually closed. Complement of open set is closed. So disconnected means there exists some non-trivial closed set which is also open. And also observe that disconnected means you can always define a map like this. Define a map from X to R. Define F on any element on U equal to 0, F on any element of V equal to 1. So this map becomes continuous, right? This map becomes continuous. Why? Because F inverse 0 is open. F inverse of any open set is open. Take any open set, if it contains 0, this will give me U. If it contains 1, this will give me V. If it contains both 0, 1, that will give me U union V, which is X, again open. If it contains none of this 0 and 1, that F inverse of that set will be empty. Right. So all it becomes continuous if we define in this way, right? So disconnected imply there exists a continuous map, which maps there exists a continuous onto map from X to that 0 1. Okay, so there exists a continuous map A from that set X to this 0 1 set. 0 1 as a subspace of real number. And similarly, conversely, the converse is also true. There exists a continuous map from X to 0 1. Then continuity imply F inverse of 0, that will be open. This is discrete, right? Discrete topological space. Therefore, F inverse 0 will be open, which is, so X can be written as F inverse 0, disjoint union F inverse 1. And this is open because discreteness, this is also open because of discreteness. So X can be broken into two disjoint, two portions, okay, which are disjoint. So disconnected implies those two. So that is why connectivity is very useful. So here, real is homeomorphic to circle. Is it true? This is not true. Why this is not true? No, because just remove a point. So if we remove a point from real number, real becomes disconnected. It is broken in two parts, but circle remain connected. So that's why connectivity is always useful. So if we remove a point from real number, just remove a point, it has two portions, this and this. But whatever point you remove, it will remain connected. Right? We'll show why those are, because this circle can be thought as image of this 0 1, and we have already seen that image under continuous map is connected. So closed open 0 1 is connected. Therefore, this circle will be also connected. Okay. Now again, the same argument can be applied. Instead of so again, remove one point. So this is two are homeomorphic. If we assume those two are homeomorphic, then connectedness will be preserved. So if we remove a point, then on the circle, the corresponding point should be removed, right? And the same homeomorphism, suppose there exists a homeomorphism, the same homeomorphism will induce another homeomorphism if we remove, so this is X, this is Y, remove a point and remove a corresponding point, then this restriction will remain homeomorphism if the first one is homeomorphism. But this cannot be possible because if we remove a point, this becomes, these two circle becomes disconnected, right? Because those two circles are connected at this point. So if we remove this point, those two becomes two different arcs, which is disconnected. But this circle, if we remove a point, this circle remain connected. There is only one portion. But for, if we remove the central point, there are two portions, which is disconnected. So by the same reason, here the answer is no. Circle is homeomorphic to r minus 0. This is true. Okay. R2 minus 0. Not really. Circle minus 0. It is actually different question. Circle minus North Pole. Circle minus, remove a point from the circle. So North Pole of the circle. If we remove that point, then that will be homeomorphic to R. Okay. So that is actually given by stereographic projection. probably you have observed in complex number that you can project everything onto this real line by this kind of projection, right? Like this. So, not this is how stereographic projection will work, and this map is actually homeomorphic. So those two are false, but this is true by stereographic projection. You can explicitly write the map. Okay. Now again the same issue. Remove a point. We'll remove the point A from this closed interval. So we get open A, closed B, which is connected, but removing any point make it disconnected. So there is another interesting problem. It says actually it is from Mukesh. So consider the equivalence relation on R2. So x comma y, this tuple is related to x dash y dash if and only if x square plus y square is same as x dash square plus y dash square. So this is nothing but identify this circle. So the points belongs to the circle will give me the same radius, right? Same radius square. So those 2 points will be identified. So pretend this circle as a singleton point. Okay. If the radius are same, those two are identified. So it is like, so that circle is identified. Similarly, those concentrics identify all those kind of circles. Then uh, R2 modulo this relation, this quotient space is homeomorphic to option A, R, option B, S1, option C, 0 infinity. Which of the following is correct? So we have earlier we have seen one way to see something is quotient or quotient map or not. We can use the property of retract. If a map is a retract map, then that map is actually a quotient map. So consider this map. Consider if maps R2 to R defined by f of x comma y is x squared plus y squared. Okay. Consider this map. Now we note that uh, so this is continuous map, which is continuous. Polynomial map is always continuous. Consider another map, another continuous map. J or I, whatever you say, J from this closed 0 comma infinity to R defined by J of x equal to root x. So those two are well defined continuous. Now can we see that F compose J? It is actually identity on this interval. So let us see. F compose J on X. So first apply J, it will give me root X. So F applied on root X. Sorry, this is not root X. That should be some. Okay, yes, it is okay. This is actually R2 root X comma 0. Sorry. Otherwise, we cannot take composition. Domain and codomains, those are not matching. Then F compose J is actually identity. F applied on root x comma 0, by definition, this is actually root x whole square, which is x plus 0 whole square. So it is x. Therefore, F compose J is identity. This is the verification. Those two are continuous map. Then by previous day's observation, F is a quotient map. Quotient map. Right? F is quotient map. Then from the discussion, we know that if F is quotient map, then it factors through the relation, right? And the relation here, it is given by x related to y, if and only if fx is related to fy. Maybe x and x does, right? X and x does. Fx is related to fx does. So, or probably z, since we are denoting probably v vector notation, v dash are related, fv is related to fv dash. That is saying x comma y and xy dash, x dash y dash, these two are related if and only if fv. So f of x comma y, this is x square plus y square, is related to x dash square plus y dash. This is by property of quotient map, right? F is quotient map, therefore there exists a factorization like this. And moreover, we know this factorization, if we denote it by f tilde, this f tilde is homeomorphism. Since f is quotient map here, f is itself a quotient map, and this is also another quotient map. Therefore, f tilde becomes a homeomorphism. Those two become same space. Homeomorphism. What is the meaning of that? So sorry. The space is sorry about that. This is not F compose J is not identity on 0 infinity, because we can see that J maps 0 infinity to R2, but here F maps R2 to R. So we need this. So this is just modify the map. Send F from R2 to close 0 open infinity. Then this becomes identity. Now we can apply the theorem that retraction is always a quotient map. F compose G is identity, those kind of map, F is called retraction. Okay, so if is now we can say F is quotient map. Otherwise, this is not an identity map. This is just inclusion. So F is quotient. So we can now apply the theorem, which using that theorem, F is quotient. Therefore, F tilde becomes homeomorphism. Okay, this is actually universal property, that if you take a quotient map, now if we consider the relation R2, the domain modulo the relation like this. So we are identifying the fibers V and V dash are identified if this maps to the same image. Sorry, this is FV equal to FV dash. If they maps to the same image. Okay. So if we identify in this way, then it factors through this quotient. Okay. And the induced map, this becomes homeomorphic since we have chosen a quotient map here. Therefore, it is clear that R2 modulo the given relation. So we have taken the relation is same as the given relation. So this becomes a quotient, and this is homeomorphic to close zero, open infinity. So this is geometrically all those points are so consider corresponding to this. I am adding this point. This point can be thought as this whole circle. Similarly, this point denotes this circle. So the origin denotes the singleton thing, and similarly, all those points will denote the circle corresponding dash, corresponding radius. So that's why this geometrically the intention is clear that this should be actually circle. If we identify with respect to this relation, that should give me a close zero comma open infinity this space, and we have proved mathematically that this is the case. So this option is correct, and earlier we have just observed that closed zero comma open infinity, this cannot be homeomorphic to circle. Okay, just remove 2 point, remove 1 point. This becomes disjoint, but this remains connected. So this cannot be homeomorphic to S1, and closed zero open infinity, this cannot be also homeomorphic to R because remove the point 0. So this remain connected, but this will become disconnected. So those are some interesting examples. So let me stop here. We'll meet on the next Friday. Bye. Is there any question? If not, let us stop. Thank you.